Klaus, you're on.
Okay, thank you, Potsena. Thank you for everybody who is attending. I don't see you and I don't know how many you are, but I hope you're all happy and you slept well. It's interesting these times. So I think each of us has a special Corona story, and I maybe want to start by telling you my little Corona story. I had my birthday in November, and I received a new coffee machine as a present. And that's my Corona project. It's fabulous. It's a fantastic coffee machine. And every morning I'm enjoying 1 or 2 coffees now. So rather than spending my time in commuting to work, I have extra time of enjoying my coffee. That's a new quality of life. Of course, there are many things that are not so good as before, but that is something that is good. So I hope all of you have something like that. So for today, I thought I covered 2 topics. And one of them is a specific example of a novel qubit. I tell you right away, it's a very crude qubit and it doesn't behave yet the way it should, but it has the potential to become a very good qubit. And then we do a little break halfway, and then I focus on a new experimental tool to investigate qubits, semiconductor qubits. That's the second half. Okay, so this first part is about bilayer graphene. And I understand that many of you work on graphene. I mean, graphene and carbon-related materials have been a big topic in many labs around the world. And I want to focus on one very specific aspect on that and why it is promising to be used as a qubit. So let me start out with a slide that is actually a few years old. So what you see on the lower right is a piece of graphene, so a monolayer of carbon atoms arranged in honeycomb lattice. And this piece of graphene has been cut, as you see here. There's been cut into various pieces. So you see where there's the dark black. That's where the graphene has been etched away. And in the grayish areas, this is where the graphene is still intact. And you see the bar here, 100 nanometers or so. And now you can think of this like this is a macroscopic source contact on the left and drain on the right. And in the middle, there's a little island. This is the quantum dot that we defined yesterday. And you could imagine that there's a little, somehow I hear an echo or so. Do you also hear that? Okay.
I can sometimes hear a little feedback, yes. Yeah. I'm trying to find out if someone is not unmuted.
Yeah. Okay, thanks. So let's assume you have this little electron here in the center, and this little electron has a spin that might precess around the magnetic field. And then you have tuning gates here on the top, so you can tune basically the electrostatics of this barrier, or with this gate, the electrostatics of this barrier, and with this gate, the number of carriers on the island, and then there might be a detector on the other side and so forth. So that was state of the art maybe 5 years ago. And let me remind you why this is interesting to investigate. We want to build spin qubits. That means we want to isolate individual spins or maybe pairs of spins. And doing that in carbon is a good idea because 99% of naturally abundant carbon is carbon-12, and that has no nuclear spin. So you have very weak hyperfine coupling. And the next thing is that carbon is a very light element, which means that the spin-orbit interaction is weak. And that's another reason why one expects long spin coherence times. These are all theoretical expectations that have not been verified by experiment yet. So let's look at this sample that I just showed you, and let's just measure the current between source and drain through this little island. And we plot this as a current or conductance. And we do that as a function of an overall backgate of the sample. So it's a gate that tunes the overall chemical potential in the entire sample. And what you see is the following. You see there is conductance or current flowing. The current is suppressed over some finite region, and then it increases again. So you see the schematics For single layer graphene, we expect this Dirac-like dispersion, E versus K. And you see here in this right-hand side, it's filled somewhere in the conduction band. So the Fermi level, that's the energy where all the filled states are below. In this case, all the blue scale states. So that would be electron conduction. That's why current goes up. And then on the left-hand side, you just put the Fermi level back down in the valence band, and that's hole conduction. And of course, somewhere in between, the Fermi level has to be at this Dirac point where the density of states vanishes, at least for a 2D system. But now you see it's not just one point where the conductance vanishes, but it's a whole range of gate voltages or energies where this happens. Now let's do another experiment, which is just a symbol constriction. So now I apologize for the color scale. So the black area is again where the graphene has been removed, and the grayish areas where the graphene is still there. So you see the current goes from a macroscopic region of graphene through a narrow region through a macroscopic region of graphene. And down here you see conductance versus spec gate, and it looks actually very much the same as on the left. And there's no dot here. It's just a narrow piece of graphene, narrower than, say, 50 nanometers or so. So what is the reason for the suppression of the conductance here, and what are these resonances in here? So these resonances could be due to dirt. And one way of looking at that is using an AFM. So what you see here on the left-hand side is a graphene constriction. And this graphene constriction is exposed to air and has all kinds of contaminants on top. So what we have done is we have taken an AFM tip and we have scratched all the dirt away. So you see the dirt accumulates on the top and on the bottom, but in this area, we basically hardly see any dirt. On the right-hand side, you see another piece, which is not quite as clean. There's some dirt there. So we would argue that this one is clean. This is not so clean. But of course, we all know that there are contaminants that we don't see in the AFM. For example, there could be hydrogen atoms that don't show up in AFM contrast, but still change the electronic behavior of these systems. So let's see what happens if we measure one of those clean devices. And what you see again is the conductance versus the backgate voltage. Note that here we have a logarithmic scale. This is why this broad minimum that we saw before is a little bit more peaked now. And what we try to understand is where this minimum comes from and whether we can make it narrower by making the system cleaner. And one way of making it cleaner is, for example, by changing the substrate. Silicon dioxide is an amorphous oxide that has lots of charge traps. We put the boron nitride below the graphene, which is a very clean insulator. And you see the black and the red curve, and they basically look the same. So no matter how clean we make our device, we always see this region of suppressed conductance, and we find this over an extended energy range. So this is not what you want for a well-defined tunneling barrier, which you need in order to build a controllable quantum dot. So the conclusion from that is, at least from what we can tell, we can try to make things as clean as possible. It never gets better, as you see here. And the reason for that is the following. Here again, on the bottom, you see an AFM image of such a constriction. The edges look rather nice, but of course, the edges are atomically rough. We don't have atomic resolution here with this AFM. And this sample is produced by using electron beam lithography and dry edging. So it's a brute force top-down technology that might have a resolution of the order of 10 nanometers or something like that, which is, of course, a length scale much larger than the atomic scales. So if you had the possibility to look in detail at these edges, they're very rough. And the wave function or the electronic system in graphene goes actually all the way to the edge of the graphene flake. And if the edge is rough, there will be localized states. So what we conclude is, no matter what we do, clean boron nitride or dirty silicon dioxide, the electronic transport looks the same. So it's not the disorder in the bulk that actually plays the dominant role, it's the disorder at the edge. And this disorder is just impossible to control by top-down technology. There are ways to do that, maybe in chemistry. There are chemists that can make excellent graphene ribbons with perfect zigzag edges or armchair edges. These ribbons, however, are so small that you can basically not attach contacts to them. But just for the sake of the principle, you can do that in chemistry, and you can take an AFM or STM and really see that the edges are atomically precise. But that's not a useful device, at least not yet, to do electronic transport. So we need to get rid of these rough edges, and one way is to go to electrostatically defined edges. As it is done, for example, do I hear a few things here? So somebody seems to have some background, okay. So, you know, yesterday I told you about gallium arsenide and silicon and so forth, where these quantum dots are defined electrostatically. And of course, everything that is done electrostatically is sort of smooth because it's defined by electric fields. And while the gate electrons themselves are, of course, also produced by top-down technology, so they have rough edges, all of these electric fields, they're screened out and they become smooth once they arrive at the location of the quantum dot itself. But if you use single layer graphene, you cannot define quantum devices just by a gate. And the reason is the dispersion, this linear dispersion, the Dirac dispersion that I think all of you know, if you move your energy, that's what you do with a gate electrode, there is never a gap. And because there is never a gap, you can never produce a region without charge by just gating. In gallium arsenide, you can move the Fermi level into the gap, and then there are no mobile charges. Same in silicon, same in indium arsenide, and so forth. For graphene, it doesn't work. So you cannot build gate-defined quantum devices because there's no gap. So if we move to bilayer graphene, these are two layers of graphene stacked on top of each other. This is what is called Bernal stacking. So that means that the carbon atoms in the second layer are positioned above the center of a hexagon of the bottom layer, at least every second atom. And what that means is that you start having two single layer devices that are vertically coupled. And what that means is that at the Dirac point, or charge neutrality, you get a parabolic dispersion. It's not linear anymore as here, but if you look here at low energy, the dispersion becomes linear, quadratic, excuse me, but there's still no gap. So what you can do is now you can apply a vertical electric field across these two layers. And by applying a vertical electric field, you break the symmetry between the two layers. And what happens is that you open up a gap here. And the magnitude of that gap can be controlled by the electric field. On top of that, the dispersion is not parabolic anymore, but it has a so-called Mexican hat dispersion, as it is called. So how do we test this now in a transport experiment? So here is our stack that we assemble. This is now not MBE. This is done by sticky tape, by picking up flakes, by putting flakes on top of each other, and then by using e-beam lithography, etching, and metallization to make contacts and stuff like that. So we start out with the usual thing. We have a silicon backgate. We have that doped silicon, silicon dioxide. Then we put down a layer of boron nitride. This is something that we get from our friends in Japan. They are experts in that. Very high quality boron nitride. I would claim it's one of the best insulators in the world, also because it's crystalline and anamorphous. And then you put a layer of bilayer graphene on top, and you deposit metal, source, and drain contacts. Now you cover this with another layer of boron nitride. So the bilayer graphene is encapsulated between two layers of boron nitride. And for example, you place a top gate across this entire device. Now what you can do is you can tune the carrier density in this bilayer graphene by applying a voltage to the back gate. But of course, there's this region here with a top gate where you can also apply a voltage from the top. So basically in this region, you can apply a vertical electric field by applying voltages to top and back gate. And you can not only apply an electric field, but you can also apply these fields relative to the chemical potential in the bilayer graphene. And therefore, you can position the Fermi level in this gap and outside this gap. So let's see what happens to transport. And I show you here some data from the group in Manchester of Andre Gein, which is from about 3 years ago. And I think 3 years ago, all of us suffered from a similar problem. So what you see on the vertical axis is the resistance of the device. You see here exponential scale, 10 to the 3 ohm, 10 to the 4, up to the 10 to the 7. And on the horizontal scale, you see what is called the displacement field. So that's the electrical field applied across this piece of bilayer graphene. And look at the numbers here. These days, we can go up to something like 1.5 up to 2 volts per nanometer. These are gigantic electric fields. And if you look at the resistance of bilayer graphene as a function of this field, you see it starts increasing. Let me remind you that no displacement field means no gap. So there's a small resistance. In this case, it's of the order of kilo ohms. And then you start opening this band gap while keeping the Fermi level in this band gap. And then the resistance starts rising, and it rises very steeply from kilo ohm to 10 kilo ohm. But then you see it starts saturating. It doesn't increase any further. So what happens is you open your gap more and more and more, but your resistance doesn't increase any further. And what they did is they not only measured a Hall bar, which is the blue and the red curve, but they also measured Corbino geometry, meaning they had a circular device with a contact in the center and a big contact on the outside. And for this geometry, in a radial direction, they could actually increase the resistance. And so they concluded from that there must be some leakage at the edges, which plays a role in Hall bars, but not in Corbino geometries. And if that is the case, then it's difficult to build a quantum device because any quantum device has lots of edges. And that's where many of us were stuck about 3 years ago. But the important thing is the following. Here I'm showing you the same device I have shown you before. And now what you do is you add a graphite backgate. So it's exactly the same device as before, but there's an additional graphite backgate. So graphite is just many layers of graphene, 10, 20 layers. If you do your stacking procedure with boron nitride and graphene, then you find many flakes on your substrate. So you actually have to look for the single layer ones and the bilayer ones, but there are many that are much thicker. And those you pick up, and one of those becomes the graphite backgate. And it has turned out that this plays an enormous difference. It has been shown, for example, for people who measure fractional quantum Hall effect, that the quality becomes much better if you position your sample on this graphite backgate. And I think in the end, everybody uses that technique, but nobody really knows why it works as well as it works. There are various reasons why this is the case, and nobody, I think, has really verified that which reason is the relevant one. Let me just give you a few of them. So we all know, as I said before, silicon dioxide is an amorphous insulator, and it has charge traps. So basically, there are local charge fluctuations and therefore electric field fluctuations. So if you position your graphene relatively close to these fluctuating charges, you induce a fluctuating potential that can give rise to localization and to disorder. Graphite, on the other hand, can be atomically flat. It has a conductance which is comparable to the conductance of the best metals. So you have a very flat conducting substrate that screens everything that's below here, and therefore all of these potential fluctuations should at least be much weaker. That's one reason why this probably works. Another reason is the following. The thickness of this silicon dioxide is typically 270 nanometers. That has historical reasons. It's a thickness with which you can see the layers on top in an optical microscope. That's just a consequence of optical spectroscopy. So that means the backgate is 270 nanometers away or more from the graphene. That means any field that you apply to a device that is smaller than this distance will have a lot of fringing fields from the side. It's not a plate capacitor anymore. And these fringing fields can modify the edges. Now, with the graphite backgate, you see the distance between the graphene and the gate is only given by the distance of the boron nitride. In our case, that's around 10 to 20 nanometers. So more than 10 times less than the thickness of the silicon dioxide. So it's almost a plate capacitor, even if this gate is 100 nanometers in size. And actually this works down to a thickness of boron nitride of 2 monolayers, less than a nanometer. So you can keep basically the electrostatics of the plate capacitor down to small sizes for the quantum device. That's another reason why this works. Okay, now you can do the following. Rather than using a gate that goes all the way across, you just use a gate that covers the left and the right and leaves something uncovered in the center. So now, if you apply vertical electric fields just with these split gates and position the Fermi level in the gap, then the current has to flow through this channel because the areas below those yellow gates is insulating. That's another thing that can be done in gallium arsenide, and we will have a look into that. So then you can cover it with another insulator, which is in our case ALD grown aluminum oxide. That's not a good insulator, but it doesn't matter because it's removed from the graphene. And then you have yet another gate to control the chemical potential right in this little channel in the center. So let's have a look first at what happens if you have a uniform top gate and you measure the resistance between source and drain. So on the right-hand side, you see the resistance measured as a function of 1 over T. You see this is logarithmic resistance versus 1 over T, so it's an Arrhenius plot to extract an energy. And you see it's exponential, and it goes up actually to 10 to the 10 ohms. That's 10 gigaohms. That's typically, if you have two wires going into your cryostat that are disconnected from each other, that's the leakage resistance of two wires. So probably the sample has an even higher resistance, but this is our measurement setup. If you take the exponential behavior here for high temperatures, you get a gap size of 55 millielectron volts, which is roughly what you expect for bilayer graphene if you apply such an electric field. So we get very high resistances. Remember what I showed you before. For this Manchester data, they had a leveling off at 10 kilo ohms. 10 kilo ohms is way down here, but now we can go 6 orders of magnitude higher. So it's a super high resistance, which is what we need. Now the same thing for the split gate device. You see, this is a conductance map. The two axes here are the back gate and the top gate. The color scale is the resistance of the device. Note that on the left-hand side, this is a logarithmic scale, the color scale. On the right-hand side, it's a linear scale. And the reason is the resistances don't get very high because electrons can always traverse through this open channel in the center. So now, as I said, we put this additional top gate there. And what we find is that the conductance as a function of this little gate voltage on top, all the other gates are fixed. Back gate is fixed. Split gates are fixed so that you get your gap behavior. You see that the device can be pinched off, zero conductance, and then it starts opening up, and then you see these wonderful plateaus here. Now, I expect that all of you heard about quantized conductance in one-dimensional systems. That was discovered some 30 years ago in gallium arsenide, and it is well explained by the fact that the density of states in a 1D systems with parabolic dispersion is proportional to 1 over the square root of the energy. So if you calculate the conductance, you take density of states times velocity. Density of states is 1 over the square root of the energy. Velocity is square root of the energy, so they cancel out in one dimension, and therefore the conductance is quantized, and it only changes when you add a new conductance channel, when you open your constriction, and a new channel can be filled depending on the position of the Fermi energy. Now in gallium arsenide, the plateaus are positioned in units of 2e squared over h, and the 2 comes from the two-fold spin degeneracy. Now here you see they are positioned in units of 4 e squared over h, and that directly reflects the fact that in graphene you have another factor of 2 degeneracy. You have 2 for spin and 2 for valley. There are 2 equivalent valleys in K space. Actually, it goes back to the fact that if you take the hexagonal, the honeycomb lattice in real space, the primitive unit cell has 2 atoms. You cannot make a primitive unit cell that only has 1 atom for the honeycomb lattice. And because you have 2 atoms in real space, you get a 2-fold degeneracy in K-space, and that gives rise to this additional factor of 2 for the value of the conductance plateaus. Now, I should say that many people over the years have tried to see this quantized conductance with more or less success, and I think finally we can nail it down. And the reason is that we can control the confinement electrostatically and no longer rely on disordered edges. Okay, now let me quickly go back 30 years when this was discovered in gallium arsenide. So you see here conductance as a function of gate voltage. This was a paper by Bart van Wees. It was, I think, his PhD thesis. And you see very nicely the plateaus as they show up in units of 2e² over h. I think this is textbook material today. Now, this can be understood in a fairly straightforward manner. So you have this split gate electrode, and this split gate electrode leads to a confining potential. And because all of this is electrostatics, in first approximation, you could say this is an harmonic oscillator. So the y direction is the direction perpendicular to the direction of current flow and the direction of the confinement. Now, if you apply a perpendicular magnetic field, I spare you writing down the Hamiltonian, because everything is parabolic. The magnetic field enters in a parabolic fashion, at least if you take the Landau gauge. The potential is parabolic. You can solve the Hamiltonian analytically, and you find that the energy levels are given by h bar omega times n plus 1 over 2. And the omega becomes now a function of magnetic field. And you see it's the expression is given here, omega c squared. Omega c is the cyclotron frequency, which is E charge times magnetic field over effective mass. And omega 0 is just the confinement potential. So if the confinement potential, if the magnetic field is 0, let's start this way, then this omega is just the confinement potential. And if you go to very high magnetic fields, much larger than the omega 0, then the energy is just given by h bar omega z, like the Landau level energy. Okay, what do you see in an experiment? You see the conductance here as a function of gate voltage. You see the zero magnetic field trace that I showed to you before. You quantize plateaus in units of 2e² over h. And now you increase the magnetic field, and you see that these plateaus shift to higher gate voltage, and they become much wider, and at high magnetic fields, there's a continuous turnover from being electrostatically defined to magnetically defined, and you reach the quantum Hall regime. So this is what happens basically for gallium arsenide. It's a continuous transition, and the reason is this equation here. The solution is almost an harmonic oscillator solution, but the relevance of the magnetic confinement and the electric confinement changes as you change magnetic field. Now let's do the same thing, the same experiment, apply a magnetic field in graphene. And I show you this because I think the data is beautiful. So again, vertical axis is magnetic field, horizontal axis is this little gate voltage, and what you see here in the color scale is now differential conductance. So when differential conductance is 0, that means that you have a plateau in conductance. So let's first look what happens at 0 magnetic field, and you see there these white regions that alternate with the gray regions. So white means derivative is 0, you're on a plateau. Gray means finite derivative, so you're between plateaus. And I put in here the numbers, it's 40, 44, 48, 52. So it changes in units of 4e² over h, as we saw and as it is expected. Now you apply a magnetic field, and one thing that you see is that each of those features splits in magnetic field, right? These are small magnetic fields. Each feature splits. They start crossing each other. And if you go to high magnetic fields, you're actually back to a situation which is very similar to 0 magnetic field. So again, you find plateaus, and the plateaus are spaced by 4e² over h. But in between, a lot of interesting stuff happens. Remember, for gallium arsenide, nothing interesting happens in between. You just go from plateaus at low magnetic fields, and the plateaus just get wider as you increase magnetic field. Here you get a lot of crossings. So we had this data from various samples. I think we had it for 1 or 2 years and we could not understand it. And because I think the explanation is so wonderful, let me quickly walk you through it. And there are a few equations that are not that important, but I note them down anyway, because once you know them, you can actually solve them as an experimentalist. So let's have a look, for example, what happens at this state n equal to 44. You see this state splits up in the blue and the green one. And let's look where it ends up at high magnetic field. So the state n equal to 44 starts participating with state 40 and 48. So the state with a given quantum number at zero magnetic field has different quantum numbers at high magnetic fields. How is that possible? You see, these are these, you get plus or minus 4. So what you do is you write down the Hamiltonian. So that's a Hamiltonian for bilayer graphene. It's known in the literature. It has very few parameters. It has the delta, that's the gap, that depends on the electric field. And then it has band structure parameters that are well known. These are the coupling constants of the various atoms in tight binding. And it's a 4x4 Hamiltonian because you have 2 layers and each layer has 2 values. And then you can use a basis state, and you can imagine it's a 4x4 matrix, so you can plug into the computer and you solve it. And the theory goes back to McCann and Falco. So now we don't have a homogeneous layer of bilayer graphene, but the gap itself has a spatial dependence. So when you go through the constriction, the gap itself is spatially dependent. And we know how from electrostatics, roughly in a parabolic fashion. In addition, there's a confinement potential, which also has a spatial dependence that we can also model. So once we have those, we can still solve that equation. And what we find is that there is something called the Berry phase in bilayer graphene. What that basically means is that as electrons move around in K-space, they go around one of those Mexican hat-like features, they accumulate a phase. And this is a topological phase. So, and what that leads to is it looks like an orbital moment. And an orbital moment, as we know, if you apply a magnetic field, can acquire an orbital magnetic moment. So we have orbital degrees of freedom that don't exist in standard semiconductors, in particular gallium arsenide or indium arsenide or the standard ones, but that show directly up here in graphene. What that means is at zero magnetic fields, whether you go clockwise or counterclockwise doesn't make a difference. Once you apply a magnetic field, it makes a difference. And that's the reason why each state, which is twofold degenerate for the Valley degree of freedom, these Valley degrees of freedom split apart linearly, and it is a little bit like a Zeeman effect, but not coupling to the spin, but to the orbital degree of freedom. And the equations are here, and you can solve that, and that has been done by Angelika Knote and Volodya Falkov from Manchester. And the calculation is on the left-hand side. Vertical axis is magnetic field, horizontal axis is energy. These are the energy states in such a confined geometry. They did not include spin in their calculation. That's why they miss a factor of 2 in degeneracies. But what you nicely see is each state splits in 2 states as you apply a magnetic field. And what you also nicely see, let's, for example, look here, look at the red state. It moves up and joins another blue state here from the next nearest neighbor. And the blue state here joins another red state, not for the lowest 2, but for the other ones. Now, maybe for the specialists, you see, there are 2 particular states. These are the 2 low-lying blue states. And what that is the following. So Landau levels in graphene are 4-fold degenerate, again, because of Valley and spin. Now there is a Landau level at 0 energy, and that is half composed of electrons and half composed of holes. Now, that leads to an 8-fold degeneracy. You get the standard 4 plus electron hole makes 8-fold. Now what we do here is we split electrons and holes, we open a gap. So each of those Landau levels is 2-fold degenerate. And because we don't consider spin here, 4-fold, if we don't consider spin, it's 2-fold. So these 2 states, the blue states on the left that move down in energy as you apply magnetic field, these end up being the low-lying zero energy Landau level in bilayer graphene. Okay, that's a detail for bilayer graphene. Now, let's have a look at the energy scales. So here is the Mexican head dispersion schematically. There's a band gap here that depends on the applied field. It's of the order of 100 millivolts for fields that you apply of the order of 1 volt per nanometer. Now, if you blow this up, the bottom part here of the conduction band, it looks like that. It really looks like a Mexican head. And that is the reason for these topological effects. Actually, if you look in detail and you go to higher energy, there's an additional effect in the band structure, which is trigonal warping, which means it's not completely round, but it has a triangular shape. But that's yet another detail, which actually plays a role in experiment, as we will see later. Okay, so I think what we have learned is that you can build tunable tunnel barriers in graphene, in bilayer graphene. You can pinch them off, and you can actually see features of the topological band structure directly by measuring quantized conductance. Now we want to build qubits. We are far from qubits. So how can we build quantum dots with that? So here is the schematic. It's the same as before: graphite backgate, bilayer graphene, split gates on top. The green gates are the split gates. Now we apply a voltage between the green and the orange gate. So they are on top and on the bottom of this bilayer graphene. That means we open a gap locally and we position the Fermi energy in the gap. That means if the current wants to flow between these two contacts, it has to flow through this channel in the center. And then we have on top yet, so all the insulators are left out here for clarity reasons. So now you take this little blue gate here that allows you to locally position your Fermi energy. And there are many such gates, and you will understand in a minute why. So what's happening? Here's a schematic on the right-hand side. So here's a sample that is stoped to be p-type. So we apply basically a positive backgate voltage to the device. So we have p-type carriers in the graphene. Then we have the two split gates. These are the blue dashed lines. We gap the material, position the Fermi energy in the gap, so there's no transport here. And the red gate is the one on top. Now let's just tune this little red gate, and that's the horizontal axis here. And you see the situation, if this gate is close to 0, you see the band structure here on the bottom. There's this Mexican head band structure. You see the Fermi level. Fermi level lies in the valence band, and current flows. Conductance is finite. Now, we apply a more positive voltage here to this little red dashed gate. And what's happening is that now we position the Fermi level in the gap just in this little region here, just in this region here. And that means that the conductance is suppressed. So this is very similar to what I've shown you before. That's the pinch of this local region. But what we can do is we can go further. We can now induce electrons here. So we keep going with this gate voltage, and we pull down the conduction band, and we start populating the very first states in the conduction band. And what you see is, and you know this already, these are very sharp Coulomb resonances. So we have filled in one electron after the other in this local potential minimum for electrons. And the interesting thing is now the tunneling barriers are actually p-n junctions. So we have a p-type region around. This is the bluish one. We have n states, a small number of electrons here, and they are confined by p-n junctions, which is very different to what we know from semiconductors. In semiconductors, in principle, you could do that, but if your band gap is 1.5 electron volts, like in gallium arsenide, you basically have humongous barriers to overcome this 1.5 electron volt, and therefore you cannot confine carriers on a very small scale. But here it works. Okay. So now look at this. That means we fill in the first electron, second, third, fourth. And you already see that something else is happening for 5, 6, and 7. That's obvious from just looking at this data. Another thing is, this is all gate defined. So what we can do is we can reverse all the voltages. We can do n-type on the outside. we can do a little hole island here, and look what happens. Rather than loading in electrons, we load in holes. So we can directly switch between a hole and an electron quantum dot in the very same device, just by playing with the voltages. Again, this is something basically impossible for semiconductors because the gaps are too large. But here the gap is order of magnitude 50 to 100 millivolts. The energy scales in the dot are 1 to 10 millielectron volts, and therefore we can go from holes to electrons in the very same device. Now let's look a little higher. Let's fill in more electrons. So you see no electrons, then you see 1, 2, 3, 4. Large gap. So we see some gaps here, and then a larger gap for 4. And then we fill in another 8. You see there are 8 peaks, larger gap. Then we fill in another 12, more gaps. So the lower scale plot shows you the distance between peaks. And you see the distance becomes large for the fourth electron, for the 12th, and for the 24th. So that's reminiscent of what you see in the periodic table. But what's going on here? What's going on in graphene? Well, we have another degree of freedom. We have the valley degree of freedom that plays a role. And we have to understand how the orbital states are filled by these electrons. So in this particular case, the quantum dot is almost round. It's not never perfectly round, but almost round. What that means is that if you see the first orbital state is an S state. And you can fill that first orbital state with 4 electrons because you have a factor of 2 for spin and a factor of 2 for valley. So the first 4 go into the S state of the dot. The next state is the P state. The P state can be along Px or Py. They are degenerate in case the system is circular, or at least it has a symmetry in X and Y. And that's why you basically look at this plot over here. That's a calculation again by Angelika Knote. This is no spin degeneracy, no valley degeneracy, just calculating the orbital states. So you see that's the first state, that's the S state. Then you have 2 P states. They are degenerate. They have the same energy when you fill them. And then things get more complicated as you go up. Now you look at the same calculation, but for different parameters. I spare you the details. And you see the first 3 states are degenerate, the next 3 are degenerate, and so forth. And the reason for that is, as I told you before, that the dispersion is not circular, but actually has triangular pockets because you have a hexagonal lattice in real space. So actually the wave function doesn't look like a single maximum here, but 3 maxima in the dot. And in this case, you have an additional 3-fold degeneracy that comes from trigonal warping. So now let's go back to the data. What does that mean? That means the first 4 electrons, they go into the S state. And you have 4 because you have 2-fold spin and 2-fold valley degeneracy. Now the next 8 electrons, they go into the 2p states. And there you have an 8-fold degeneracy, 2 for valley, 2 for spin, and 2 for the orbital p states. That's 2 times 2 times 2, that's 8. That is electron number 5 to 12. Now, as you fill in electrons in your system, they start screening the potential and it becomes softer. And then this trigonal warping becomes important. So now your degeneracy becomes 2 for spin, 2 for valley, and 3 because you have this triangular symmetry. So that's 2 times 2 is 4, times 3 is 12. So for electron number 13 to 24, you're filling these new states. So you see, it's fantastic that we can see that. Impossible to see gallium arsenide because you miss their corresponding degrees of freedom. Now we think about the periodic table. We know there's first shell and second shell and so forth. And you know that for hydrogen, you fill in the first electron, for helium, the next, with the opposite spin, and then you go to the next row in the periodic table. So now let's look at the S shell. How are the electrons filled in? And we monitor basically how these Coulomb resonances behave as a function of a field which is only in the plane of the sample. But it's only in the plane of the sample, it can only couple to spins, not orbital degrees of freedom. And you see the first 2 electrons, they shift downwards in energy and magnetic field. The next 2 move up. The dashed line is what you would calculate if you assume a G factor of 2, and that is the G factor for electrons in any carbon-based material. So a G factor of 2 for weak spin orbit interaction. You see, the first 2 spins go on in parallel, the next 2 spins go on with the opposite direction, anti-parallel. So that means we are filling in 2 electrons with the same spin direction, but opposite Valley degree of freedom. And then we are filling in the next 2 electrons with the opposite spin direction compared to the first 2, but the 2 have opposite Valley quantum number. And now we go to the P shell, and you see again the first 4 peaks go to the left, the next 4 peaks go to the right. So now if we just plot the slope of these peaks and convert it to a G factor, you see the first 2 have -2, the next 2 have +2. That's 2 spin down electrons, 2 spin up electrons. And then we have 4 spin down, 4 spin up. That's the P shell. And then we go to this novel state, which has a threefold degeneracy because of trigonal warping. And you see it gets complicated. And the reason for that is that now we have many electrons in our system. In electron-electron interactions play a role. And you know that also in the periodic table that happens. Exchange plays a role, and the filling becomes more complex. So we understand most of this, and there are many things that we still need to understand. So let me see, we can tune the Valley splitting. I just want to highlight maybe one thing here, which is completely different, but which tells you the power of this graphene with gate electrodes. So you have all heard that there is superconductivity in magic angle twisted bilayer graphene. I think this was the highlight in condensed matter physics 2 years ago, discovered by the MIT group. We take this magic angle bilayer graphene, which is yet a more complex band structure, spare you the details, you can make it superconducting. So here is this twisted bilayer graphene that's encapsulated in boron nitride, graphite backgate, top gates, same as what you've seen before. And now we build a device where we can switch on and off the superconductivity locally by gates. And this is a complicated gate arrangement. And basically, we have a central gate that makes the system locally insulating, and we have 2 outer gates that make it superconducting. And that means building a Josephson junction. And the Josephson junction, I show you the data right away here. So that's the IV trace of this Josephson junction. So you see that it becomes basically the current can flow without any voltage over a finite range until you come to the saturation current. And you see these steps here that are related to Shapiro steps if you apply high frequency. And here is the map as a function of the power of the high frequency, and these are Shapiro steps. So it's disconnected, completely disconnected from the quantum dots I talked about before, but it shows you the power that is in this graphene system, that you can play with the technology and you can actually make superconducting devices, quantum dot devices, and then you can dream ahead and say, let's combine that. So I think you probably are exhausted. At least I am exhausted. Let me tell you who did all of that work. So Hiski was a PhD student 3-4 years ago. She was the pioneer who actually discovered the technology to make all of this possible. Marius did the quantum dots. Caroline did scanning gate. I hope you recognize Veronica Stara, who is with us now for 3 months and will stay a little longer. And she's from your university, and she's involved in the graphene quantum dot project. She's trying to understand how does all of that depend on the thickness of boron nitride, and can we make it even much better this way? And let me not go through the other names, but let me just show, I think this is nice because half of the team is female, which is very unusual, and we are very proud of that. Okay, let me make a break here, and maybe we can directly, if people have questions to this, maybe we can have a question session right away. Are there questions?
Okay, I would have one question.
Please.
It seems that you have solved all the practical experimental problem with silicon dioxide charge traps by hexagonal boron nitride. Are there any other practical problems with the hexagonal boron nitride. It is only one layer thick, so it's quite thin. So from practical point of view, are there any limits there, or it's a miracle that can solve almost everything?
Okay, thanks for this question, Mira. Obviously, it cannot solve everything. So maybe I didn't say that clearly enough. In the devices that we prepare, the boron nitride is typically 10 to 20 nanometers thick, which is still thin to any oxide you use in semiconductors, but it's still that thick. And the simple reason is because you see it more easily in the optical microscope and you can pick it up more easily. What we know is that 2 or 3 monolayers should be enough for electrical insulation. We haven't actually really built a quantum device with an insulator that is only 3 monolayers thick. But I don't see a reason why it shouldn't work. It's a little harder, but we haven't done it. I really think that this boron nitride is a fantastic material. I mean, without that, we couldn't do anything, and many other groups couldn't do anything. And that is all due to these Japanese colleagues who pioneered it and distributed it all over the world. The disadvantage is, of course, it's still exfoliation technique. And I mean, Veronica can tell you probably lots of stories where she tries to pick up a boron nitride, and then you put it down and it's full of bubbles. And now you ask, how do we get rid of those bubbles to get a very flat device? And that's a piece of art and tenacity and endurance. And the yield is far, far, far from 100%. Yeah. I'm just showing you the stuff that works here. But there are many devices that don't work.
Yeah, okay, thank you. Can you estimate the rate of success with your devices?
So we are always discussing that back and forth. I think so a number like 20%. I mean, of course, the numbers get higher as one proceeds, but maybe every 5th device is interesting enough that we study it intensely in transport experiments.
Yeah, thank you for this answer, because I think it's interesting information for our students. So thank you.
Yeah, most of the times things don't work.
Yeah, thank you.
Thank you. So should we take a 3-minute break? Josena, does that make sense?
Yes, we can.
Okay, let's take a 2-3-minute break and then continue. Yeah.
Yes, we can continue.
Yeah, of course. Yeah. Okay.
Okay, good. So let me change topics completely now. Now I will tell you something about...
Just Klaus, your camera is off.
Oh, sorry. Okay now? Yeah. Okay. Change of topics, high frequency access to qubits. So this is sort of the motivational slide. What you see on the left-hand side is a schematic that comes from quantum optics. So basically the idea is you take 2 mirrors, 2 high-finesse mirrors, very good reflection properties, and you have optical resonances in this cavity. And then you position an atom, and this atom is a 2-level system. And of course, you make the 2 systems in such a way that the level transition between the 2 levels, the energy matches the energies of the photon. And then if you have an intense photon field here in this cavity that couples to this atom, that means the photon is absorbed and reabsorbed and emitted, then you can reach a regime of what is called strong coupling. So you build basically a hybrid state, which you would call, in the certain circumstances, it's half photon, half atom. And there's also the ultra-strong coupling regime and so forth. This is a workhorse for atomic physics for many years. They have it under very good control. Now, what we'd like to do is something similar. Actually, the mathematics is completely equivalent, but the technology is completely different. So think again, schematically, you recognize this is our double dot system. And the qubit, for example, is an electron hopping back and forth. So that is what we call the simplest possible charge qubit. And of course, an electron that hops back and forth, that's nothing else than an electric dipole moment, an oscillating electric dipole moment. Now, it turns out that the quantum dots are separated by, let's say, 100 nanometers, which is a huge distance, which means such an oscillating dipole moment is orders of magnitude larger than any dipole moment you can have for an atomic system. Now, the energy scales for atoms are optical frequencies. The energy scales for our quantum dots are much smaller. So they are milli-electron volts, not electron volts, but milli-electron volts. Because the energy scales are smaller, that means the corresponding photons are microwave photons, not optical photons. And that's why you build a microwave cavity, a superconducting microwave cavity. Now, these cavities have also been around for a long time, and they are used intensely for superconducting qubits. So I have a colleague at ETH, Andreas Wallraff, who is one of the pioneers in superconducting qubits and how to couple them to these resonators. And we joined forces and tried to couple quantum dots to these resonators. And now you really have to merge technologies, because there is semiconductor technology on one hand side, and then there is superconductor technology on the other hand, which in this particular case is aluminum or niobium titanium nitride, or some superconductor which allows you to make good resonators. Okay, now, how do we couple them, these resonators? So schematically, you see the microwave cavity, and schematically, you see the qubit down here. So both systems are not perfect, right? The cavity itself has a decay, and it has to have a decay because that's how you experimentally access it. You send photons in and you couple photons out. Now you want to make this coupling as weak as possible to not perturb the cavity, right? Make the lifetimes of the photons large. But there is a loss rate, and the loss rate can be engineered, but it is finite. Now, for the electron hopping between these two quantum dots, there is, of course, qubit decoherence. You can think of it in a classical way. At some point, the electron will be in one of the dots. Oscillation is gone. So I told you that this is actually one of the limits of the charged qubits, and this is something between 1 to 10 nanoseconds. So these are intrinsic properties of the cavity and of the quantum system. Now you want to couple them, and the coupling constant is called G. And you want to engineer that coupling that it exceeds or is at least as large as the decay channel. If it's smaller than the decay channels, then you will never see any coupling between the two, because the quantum state or the photon state will have decayed before you can measure the coupling. So the strong coupling regime is defined by that this coupling G is larger than any of the decay mechanisms. Now, the Hamiltonian is the so-called Jaynes-Cummings Hamiltonian, and that Hamiltonian is now used in so many fields of quantum physics. It's used by atomic physicists, by people who do nanomechanics, microwave physics, and it basically has three important terms. You see here, that's a harmonic oscillator term that describes the light field. That's a spin Hamiltonian that describes your two-level system. That could be an atomic system or a quantum dot. And this term here, proportional to G, couples the two. So these three terms are essential. And from this Hamiltonian, you can calculate what you need to do. Now, it turns out that many qubits actually have resonances in the microwave regime, and you could dream about the long microwave resonator where you have spin qubits and charge qubits and transmon qubits and Rydberg atoms that all couple to the same resonator, and you could exchange quantum information coherently. That's a dream at this point. Okay, now How do we start? And we start with gallium arsenide. Again, it's not the best material for qubits, but it's the best material to control your quantum system. So we start with a heterostructure to the electron gas below the surface. We etch this electron gas away, except for a very small region. There we make contacts. We put down gates to locally define our quantum dot at the very top of this mesostructure here. Then we come up with a superconducting resonator. In this particular case, it's a squid array resonator, but the details don't matter so much. And this has one electrode that actually connects directly to the quantum dot. So there are Josephson junctions here, and that's the real picture. So that's a resonator. So there's a microwave field resonant in this cavity here. And at the end of the cavity, you see this metallic connection, that's aluminum, that connects directly to this electrode. And this electrode connects directly to this gate electrode that is on top of one of the quantum dots. So here, this is a gate arrangement where you have the left dot and the right dot. And you see this line connects directly to the resonator. So the idea is now the following. We have a port coming in here where we can couple in microwaves to this resonator, which is shorted on the right-hand side. So it's a reflection measurement. And when we excite the resonator at its resonance frequency, we see a resonance in reflection. Now, this is a high frequency resonance. It's in the 4 to 8 gigahertz range. Now, the capacitance of this entire system, of course, also depends on this line here and this line here. Now, let's assume the quantum dot is empty. There is no electron here. Then this is just an additional piece of metal, which will change the capacitance. However, if there is an electron down here, then this oscillating electrode, remember, this is an oscillating electromagnetic field. So the voltage oscillates on this gate, and if this voltage modulates a charge, then this gives rise to an additional capacitive signal, and that means that the resonance frequency of this resonator will be changed. So the resonance frequency will depend on whether there is an electron or whether there is no electron. And not only the resonance frequency, but also the Q and so forth. Okay, now, very basic, this is our double dot. You know, there are 2 energy levels. Let's forget about spin here, just orbital states. The difference between these 2 states is what we call the energy detuning. The coupling between these 2 is the tunnel coupling. So if we come with a resonator frequency that is defined by this long red arrow, that's the resonator frequency, then you see it depends whether this resonator frequency matches the difference between the energy levels is larger or is smaller. So now you see on the horizontal axis the detuning of the system. On the vertical axis, you see the energy scales that are relevant. So the red line is the qubit frequency. That's the frequency that depends on detuning. If detuning is 0, then the 2 states left and right are the same, but because of tunnel coupling, they split into an odd and even state. And that's 2T. That's this energy difference. Now, if you tune these 2 states in the 2 dots apart from each other, then you go along this line and you see the coupling, the tunnel coupling becomes irrelevant once the 2 states are detuned. So the red line is the qubit frequency as a function of detuning. And detuning is just a combination of gate voltages. Now let's assume there's this resonator frequency, which just crosses this dispersion relation here. Now, if you have coupling between the 2, then of course there will be an anti-crossing between these 2. The 2 systems will talk to each other. And that's what you see here directly in the experimental data. So you see the resonator frequency is around 5 gigahertz. So if we are far off resonance from the qubit, we just see the resonator. Now you hit the qubit frequency. Right here you hit it, you get this anti-crossing between the 2 lines. And that tells you that you can actually measure the qubit state by measuring the reflection properties of this resonator. So that's a result that was, I think, achieved some 8 years ago. And it was achieved by 3 groups simultaneously, by a group in Princeton, a group in Paris, and by us in Zurich. Okay, now you have a closer look at that, and you make a cut along one of those lines. You see there's this anti-crossing, these 2 lines. you can measure the width of the line and the separation of the two lines. And you can imagine the width of the line has something to do with the decay mechanisms, which I discussed before. And if the width of the line is less than the splitting of the line, then this is what we call strong coupling. That means the two systems, namely the microwave photons and the superconducting resonator, that's one system, and the coherent electron that oscillates between the two quantum dots, these two become a hybridized system in this regime where the excitation is half charge, half photon. I think that's a great success. Again, in atomic physics, that was done 20 years ago. In superconducting qubits, it was maybe done 10, 15 years ago. And now you can do that with semiconductor systems too. Now you can do qubit spectroscopy. Now, let me just put this in general terms. If you have an atom, you have discrete levels. If you have a tunable laser, you can measure various transitions in this atom, and that allows you to really understand all the details of the atom and use the levels you want to use for your quantum bit. Now, in a transport experiment, as I've discussed it before, you just measure at the Fermi energy and you have a small voltage bias maybe, but you always see what's happening at the Fermi energy. Now we have access with a microwave photon, and this particular squid array resonator that I mentioned, that can actually be tuned in frequency by tiny magnetic fields, because the squid loops, they change their impedance as a function of magnetic field. So you have a spectroscopic tool. It's like a tunable laser in the optical field, and you can probe the dispersion of the qubit. And you find very nice agreement with a very straightforward theory. So that's not surprising, but it gives a new handle. Suddenly we can do spectroscopy of the qubit. And you can also measure the coherence properties. So basically you measure the height of this peak as a function of the power that you send into your resonator. And obviously if you send many photons, you start broadening your line. You get decoherence. And that's what you see on the right-hand side. So you see basically the width as a function of the power. And you see when the extrapolation of this line to zero power, that's the natural line width of your system. So we are approaching language that is used in optics. Okay, how about spins? Well, that's a complicated question because spins are magnetic dipole moments. And magnetic dipole moments don't couple to fluctuating electric fields. They couple to fluctuating magnetic fields. But the magnetic dipole coupling is orders of magnitude weaker than electric dipole coupling. That's actually the reason why spins have such a long lifetime. So just coupling a microwave resonator to a spin qubit doesn't work. I mean, I shouldn't say it doesn't work. It's a super hard experiment because the coupling is so weak. So what you do is you basically encode your information, your spin information in a different way. And okay, let me go through that. That's not relevant. I show you a very special spin qubit. And this spin qubit is an Rx qubit. So I'll walk you through that. Sorry for all this nuisance here. That's not what we built. So what we do is now we build a very complicated qubit. The qubit is a triple quantum dot with 3 electrons. So in gallium arsenide, this is actually easy to do. Gallium arsenide is such a nice material system. You say 3 electrons and 3 dots. You make the technology in the clean room and it works. Now, once you have 3 electrons, these electrons have spins. And the question is, what is that spin configuration? How can we play with that? And in principle, there are 8 different spin configurations for this 1-1-1 configuration. So what we do is we do the following. Let's look at the top row here. Here we have 1 down, 2 up, down, up, and up, down. So all of these 3 spin configurations have a total spin of 1/2 up. Okay, so the total spin for all of them is the same. The Z projection in vertical direction is also the same, but the spin configuration is different. So you see here, the downspin is in the left, here it's in the middle, here it's on the right. The charge configuration is also the same. It's a 1-1-1 charge configuration. So the spin information is encoded in the spin configuration. Now you can imagine, if you want to go from the left to the middle, what you do is you take the middle electron, take it to the left, and then take the left one and put it to the middle position. Again, I know electrons are indistinguishable particles, but in principle, that's how you do it. So in order to go from the left to the middle one, you have to go through the center configuration, which is a 2-0-1 configuration, which has a dipole moment. The 1-1-1 configuration doesn't have a dipole moment. So in order to go between the configuration, you go through an electronic state that has a dipole moment. Once it has a dipole moment, you can couple it to the resonator. So in order to couple a spin to the resonator, you have to add some charge degree of freedom, and that's how we do it. So there is exchange interaction that plays a role here. I spare you all the details. And if we do that, we can actually calculate the energy level diagram. This is called the RX qubit because exchange is relevant. We didn't invent it. Many others played with that before, but we realized it and coupled it to a resonator. And this is sort of the charge stability diagram. You see it's the 1-0-1, 1-2-0. You see all the fillings of the 3 quantum dots. And what is interesting for us is this little center here, where we have 3 electrons, 1 in each quantum dot. So, and if we blow this up, you see basically now it's already the microwave signal. So you see the frequency of our resonator. This is the detuning axis. And you see how we get a signal exactly when we go through these various configurations. On the right-hand side, you see the calculation that follows from the Hamiltonian. On the left-hand side, you see the data. There's excellent agreement. And if you make a cut through that system, you can nicely see that we can make a degeneracy point where all of these 3 1-1-1 states occur at the same set of parameters. So I understand that I'm going very fast now, but I want to give you an idea of what one can do. So if you don't understand this qubit in detail, that's perfectly fine. Just remember, it's a way of encoding spin information in a system that has no electrical dipole moment. However, the transitions between the different spin configurations requires a state that does have a dipole moment. And if you do the spectroscopy, you see again that we get 2 peaks, anti-crossings here. You see that the peak width is less than the peak splitting. Not much, just barely. But it shows you how we can couple the spin state to the microwave resonator. So this is a way of moving forward with these systems. Now, let me just show you one last result to show you how advanced this field is. I showed you this dream in the beginning that we would like to couple different quantum systems to the same resonator to exchange coherently quantum information. And especially in the field of superconducting qubits, there is quite a number of works that have demonstrated that. What we would like to do now is exchange information between a superconducting qubit and a semiconductor qubit using a coherent microwave photon. So this is the chip. You see the scale bar, 1 millimeter. This is a piece of gallium arsenide, and I will walk you through the details here. So you see, they are all bond pads here. There are microwave connectors. You see resonators here. So basically, the important part, excuse me, is this one here. Let me blow this up for you. So there is a triple quantum dot that I have explained to you, that we operate in this as an RX qubit. So these are 3 quantum dots, each one containing 1 electron with a corresponding spin orientation. So that's schematically here, source and drain contacts, tuning gates, and so forth. Then there's a squid array resonator. And the squid array resonator couples to the RX qubit. That's this coupling GRX. Then on the right-hand side, there's a superconducting qubit, which is a squid made of aluminum technology. This is what is called a transmon. This transmon is also coupled to the squid array resonator with this coupling strength GT. And then you yet see another coupling, which is this one here. That's the GR. So there is yet another resonator here that is used to read out everything. So we have different coupling parameters here that all need to be strong. So let's look at the various components individually. And what I show you here is now the resonant interaction between the various systems. So you see we have three quantum systems. It's our semiconductor qubit, it's the cavity, the superconducting cavity, and it's the transmon. All of them are tunable. Their resonance frequency is tunable. So the Rx qubit, that means playing with gates. The transmon, that means playing with tiny magnetic fields that penetrate the squid loop. And the same is true for the cavity. So now we tune the transmon off resonance, and we only have the Rx qubit and the resonator. You see the anti-crossing of the lines. You see a line scan here, and you see that the two are in resonance. Now, what we can do, strong coupling established, and we can calculate the charge coupling. Now, let's take the Rx qubit of resonance, only resonator and transmon. Again, you see an anti-crossing. It's much nicer than before. And the reason is that the transmon has a much higher coherence time than the semiconductor qubit. But you can calculate the relevant parameters and the coupling strength, and we see now that the transmon couples strongly to the resonator. So now what we do is we take all three quantum systems and we put them all at the same frequency so that they are in resonance. So you see here small anti-crossings and big anti-crossings. And that results from the coherent coupling of all three quantum systems. So you can imagine that's quite a tour de force to get all of them fabricated so that they work. So I said before, if you have a success rate of 20% per system, if you have three of them, that would never give a successful sample. So fortunately, that's why we use this technology. Gallium arsenide has a much higher success rate. Aluminum technology is established. So that's why this very, very complex system works. And then, of course, you have to also play with the tuning parameters, and the experiment is rather complex. It's all microwave spectroscopy, and it allows you to really establish this coherent coupling, which is, if you think about it, really amazing. It's the coherent coupling of a spin excitation in a triple semiconductor quantum dot to the quantum states in a superconducting qubit, which in the end is a macroscopic current that runs clockwise or counterclockwise. And these two extremely different states are coherently coupled via microwave photons in between. So that is what this experiment here establishes. And now, once you have done that, then of course, this opens the door to many other things. And you can imagine what we would like to do now, and what we are actively trying, is to not take gallium arsenide, because gallium arsenide it's not a good qubit, because spin orbit is strong, hyperfine coupling is strong, charge noise is high, but to do the same thing with graphene. And graphene, Mira mentioned it, it has, all the samples are a little piece of art, so the success rate is not that high. And that means that it's not so easy to couple and to realize these systems. But we are getting there, and we will have to see that. So the people who worked on that, let me also mention them. So Anna Stocklauser, she was the one who actually realized for the first time the strong coupling of the charge qubit. Andreas Landig was the one who realized the strong coupling of the spin qubit. Benedict is an active PhD student who still looks at a completely different qubit that I haven't talked about. And then Pasquale was a fantastic postdoc that held all of this together. And then, of course, Thomas and Andreas are professors that are also part of that team. So I just wanted to give you a glimpse of what can be done with these microwave spectroscopy. I think we have just started to explore how we can look into semiconductor quantum systems using that technique. It's very powerful, and it's important to control in order to move forward in this direction. So I think I'll stop here, and I would be very happy if some of you had some questions. So thank you very much for your attention. So are there questions? I know the last part of my talk was a tough one.
Maybe I'm not able to raise my hand, but so I will speak directly. Yeah?
Yes.
Yeah, Tomášik. Just do you have maybe, you know that, that strong coupling is a very nice effect in physics, and we are dealing with that also in our group concerning plasmonics. Yeah? But my question, is there do you see any particular, let's say, application of that effect in the field of contour of those dots, or might be there some, let's say some breakthrough, let's say, advantage and impact of that effect in that field?
So you mean beyond qubit applications, whether they're...
I mean there, but it's from the physical point of view very nice and interesting. But if you see any let's say future application of that strong coupling between in those qubits.
Well, I think there's a clear application, of course, when you think about a large-scale quantum computer.
Yeah.
Because you can imagine you build 1 dot, 2 dots, 3 dots, maybe 4, maybe 5, but you run into a topological problem with your gate lines. If each dot requires 5, 6 gates to be tuned, you cannot build 100 dots with gate lines that allow this to you. What you can do is, however, you can build local islands of, let's say, 5, 6 dots, and then they are connected coherently with a microwave resonator to another set of 5 or 6 dots. So I think we need something like that to, in the end, make a quantum processor based on semiconductors. There are other ideas, of course, on how this long-distance coherent transport of quantum information could work, but the superconducting resonators, at least as far as I know, is at this point the most promising technique. Wow. So this is from the technological point of view. But if you think about physics, I think it's what I've discussed so far are qubits that are, I mean, they're the simplest qubits you can have. It's a charge qubit. It has 2 states or something like that. If you think of your qubit more complicated, for example, the Kondo effect is an effect in condensed matter physics that relies on spin correlations. So let's assume you make strong coupling between a microwave photon and a quantum system where the quantum state arises from correlations. Then I think there is a completely new door to do physics. Or I quickly showed you this twisted bilayer graphene that gives you a superconducting state. So you could think of building a quantum dot where the quantum dot is superconducting. Now, I don't know what that means. I know what superconducting leads are. I don't know what a superconducting dot is. But you could do something like that. And you could then connect that to a resonator and measure the energy levels in that system and hopefully learn something about correlations in condensed matter physics. But that's a long way to go.
Thank you.
Yeah, thanks for the question.
And that experiment is done together with your colleague from ETH you mentioned him. Yeah? I mean, concerning that microwave technique and those oscillators and so on. Yeah.
Yes, this microwave resonator technique is completely non-trivial. As usual, once you know how it works, it's not so complicated. But if you start doing that without somebody who is an expert, that takes a long time to get started. So we couldn't do it without my colleague.
Yeah. Okay. And I'm just trying to, let's say, to extend our experience from our plasmonic area. There are resonance systems, some antennas which can also increase the magnetic field here locally. Have you tried to think also in this way to improve that interaction with spins?
So we have not done that, but I know that other people have worked on that. In particular, people in Paris have tried to couple to spins, for example, in NV centers or ensembles of NV centers.
Yeah, okay.
And there is data that this is possible, but you still need ensembles. I'm not aware of a single spin coupled to a cavity. Many spins is possible. Yeah. And it's even much harder than what we are doing here because the coupling strength is so weak.
Okay.
Yeah. Thank you.
Then, I think there is in your at ETH there is Peter Gambardella, or what's his name? Yeah, and he is also, I think, playing with, let's say, the locally enhanced magnetic fields using for EPR at atomic resolution, for instance.
Yes.
So it might be. Yeah.
Pietro,
but your frequencies are just, there are units of gigahertz, yeah? Or can you go for, are there systems with, let's say, higher energy transitions that you can go to tens of gigahertz or something like that? Would it be interesting?
So there is a technological window between basically between 4 and 8 gigahertz, and this window has various reasons. It means that's where you can make nice resonators. Also, you have good amplifiers. And amplifiers have been mostly developed in the field of astrophysics because they have also resonances in that regime. So once you go above 10 gigahertz, it becomes complicated with cabling in the cryostat. So it's all doable, but it's not just adding a source that gives you a higher frequency. You have to change your entire setup. And lower frequencies is difficult because once your frequency is less than kT, and let's say we take 100 millikelvin, so you need a gigahertz so that the energy is larger than kT. So there's a lower cutoff that makes sense, and then there's a higher cutoff which is more or less given by technology. Everything above 10 gigahertz is possible, but requires a very different approach. All the plugs in your cryostat and so wouldn't work anymore.
Thank you.
Thank you.
Okay, can I ask?
Sure.
Yeah. So of course this is very impressive, and it's nice to see the coupling between photons and solid state qubits. But of course, one objection could be that the more straightforward approach is to stay fully photonic, and that field is obviously not that developed so far. But people from Bristol, they are probably secretly working on it in PsiQuantum. So what is your opinion on this fully photonic approach? Are you afraid of them as your competitors, or you think that they will never gonna be at such level as the solid state qubits are, or these qubits are right now?
Well, I'm not afraid at all. In the contrary, the more people that work on that, the better. Of course, the optics people are usually ahead of us because they have these fantastic techniques developed over the last 20, 30 years. Microwaves are catching up, and many things can be done with microwaves these days that cannot be done with optics. But maybe I can come back to a comment that I made yesterday. So I could imagine that a future quantum information processor is built on different technologies, And optics will definitely be part of that. I mean, somehow you have to get the signal out, and that's most likely optics, because a fiber is so much easier to handle than a microwave resonator. So you have
you can't get microwave radiation to the satellite as well, right? Very easily.
Yeah, and you need to do it coherently, right? So your waveguide should be at 100 millikelvin. So, but people are working on a coherent converter from microwave to optics and back. And there are many people working on that for actually quite a number of years. There are people that use mechanical systems that have resonances in both domains that you can couple coherently. Again, people use superconducting qubits. I think there is no good technology around yet, but I'm pretty sure this will come. And then if that is possible, then one can actually use the beauty of both worlds. So I think the more successful they are in optics, the better for us, because I mean, it's not that there is a race that is over tomorrow. It's a race where we will know who the winner in 10 to 20 years. And I'm pretty sure we will have many winners, and it will be a team effort. And there's a lot of knowing and learning from each other. So I think that's a very nice situation.
Yeah, thank you
for the question.
It seems that there is no other question. So may I ask you, what's the, do you know what's the present situation with quantum technology, how is it called, flagship program within the EU? You know, what's the present state and how does it go? And is there any real chance to join? And
so I have no money from the quantum flagship. I'm part of the Graphene flagship. The quantum flagship is organized in a few big projects. There is one project on superconducting qubits, one on ion traps, one on spin qubits. Now, actually, there was a late one on spin qubits now. So you have to be part of those big consortia to really get some money from them. So if you just come as an individual researcher with a great idea, that probably doesn't fly. And these few selected projects, they are very well funded. Yeah, but it's not. You have to come with a consortium. It's not possible as an individual.
And isn't it, let's say, closer to application that maybe fundamental research is a little bit, let's say, pushed back, or is it like that, or what's your feeling?
It is definitely very much towards technology. I mean, that you have to have a goal to build 50 qubits in 2 years. That should be your goal. And the science is how you do that. But if you say, for example, you see the research that I'm doing is not so much scaling up qubits, but looking for new types of qubits. And that's a little too far off for that funding, as you say, because they're really looking for concrete applications, which I think is fine.
Thank you. Okay.
Okay, no more questions?
So if there aren't any more questions, then I would probably very much thank Klaus for sharing his knowledge on this topic with us and for preparing such a great talk. I would like to also thank everyone for participation and for your questions. And yes, thank you very much. It's been great.
Thank you.
Thank you, everybody. Have a nice day.
Very nice. Thank you, Klaus.
Bye, everybody.